All right, guys. So I'm gonna make a quick video. It's not gonna be as in depth as a normal video would be, but a lot of people are gonna be absent today, and I want to talk about 6-3 and 6-4. So getting into electrochemistry. And so I just want to touch all the quick points and show you kind of how to do things and what you're going to need to do. But you still should probably go through the PowerPoint and the guided notes if you were absent. We're probably not going to get through all of those today, so we'll be continuing those next class. But again, I wanted to have a little bit of something for you to so that you can get a start on your 6-3, 6-4 assessment and your concept check 2, Unit 6 concept check 2 in AP Classroom. Okay, so electrochemistry. So we're kind of moving on from thermo, which is delta G, delta S, delta H, temperature, thermodynamic favorability, and that kind of thing. And we're going to move towards electrochemistry. And the reason why they kind of go together is a lot of the questions that'll be asked will be, is an electrochemical reaction, is it spontaneous or not spontaneous? And one way to do that would be to find the delta G of a reaction like we normally do. But now we're going to introduce a new thing called cell potential of an oxidation reduction reaction. And if that thing, cell potential, which we'll talk about, is positive, that means it is favored. And if it's negative, that means it's not favored. So it's kind of like the flip-flop of delta G. So we know delta G negative, favored, delta G positive, not favored. Cell potential is the opposite of that. Cell potential is positive, it's favored. If cell potential is negative, it's favored. And so essentially all we're going to be doing is talking about how to get a positive cell potential, what that means, and basically how a battery works. Okay, getting electricity out of a chemical change. So it's basically converting a chemical reaction into electricity. So converting chemical energy into electrical energy. Okay, and all right. So let me flip this. All right. So if we look at if we look at electrochemistry, basically we're going to be talking about how to make a galvanic cell, which is another word for a battery. And so it's really, how do we get electricity? So if we understand that electricity is the motion of electrons across a medium, kind of like electrons bumping along a copper wire, our goal is to try to make electricity. And in chemistry, the type of reaction that involves the movement of electrons from one thing to another thing, a transfer of electrons, are oxidation reduction reactions, right? So that's why electrochemistry is basically the study of redox reactions, because in a redox reaction you have something losing electrons and something gaining electrons. So if you think about it on kind of the atomic level, electrons have to be passed from one nucleus cloud to the other nucleus cloud, right? So one atom to another atom, so electrons are transferred. And so really all you have to do is understand, like if I have something that tends to be oxidized, wants to lose electrons, and I have something that tends to be reduced, wants to gain electrons, and they bump into each other, the transfer is going to happen, right? If I take sodium and I throw it in with chlorine, when chlorine comes in contact with sodium, the chlorine is going to take the electron and sodium is going to lose the electron. But it's just going to happen right in that proximity. You're not going to have, one thing bumping in, one cloud bumping into the other cloud. You get the transfer. But the question is, how do we tap in to get electricity? And the answer is you separate the two components. So you take the thing that wants to be oxidized and the thing that wants to be reduced. And think of it this way: if you want to be oxidized, you're kind of want electrons away from you. So you have this constant pushing of electrons away from you. And if you want to be reduced, you kind of have this constant pull of electrons to you. And if you if you want to be reduced and you're constantly pulling at electrons, once an electron comes into view, you get it, right? And if you want to push electrons away from you, if you want to be oxidized, you're constantly wanting to push them away. And if something comes along that can take that electron, then you push it off onto that other thing, right? So if we separate the two things, the one thing pushing electrons away from it, the thing that's going to be oxidized, and the one thing that is pulling electrons to it, the thing that wants to get reduced, if we separate them but connect them with something that allows the flow of electrons, like a copper wire, right? Then when we connect them, the thing that wants to be oxidized is going to push electrons along the wire, and the thing that wants to be reduced at the same time is pulling those electrons to it from the wire. And what voltage is, what volts are, it's called the electromotive force. It's really it's the combination of the push-pull. So you have the push of electrons from the thing that wants to be oxidized and the pull of electrons from the thing that wants to be reduced. And the sum of that force, the push and the pull, is what voltage is, okay? And so, if you want to get electrical energy from a chemical reaction, you get an oxidation compartment, you get a reduction compartment, and you connect them with something that conducts electricity, and you'll get this combination push-pull of electrons across the wire. And the bigger the push, meaning the more likely something is going to be oxidized, the bigger the push of electrons, and the bigger the pull of electrons, so the more likely something's going to be reduced, the higher the voltage. All right, that's the whole idea. All right. So what you're going to see is, you're going to, if you look in the back of your book, and I give you a handout, you get Appendix E, which is, they're called standard reduction potentials. And notice it has the symbol E naught. That's cell potential. But if it's just showing a half reaction, all these are showing reduction reactions. These are called reduction potentials. And when you have a positive cell potential, that means whatever is being reduced in these equations is favored to be reduced. So when you have a positive reduction potential, that means that substance is going to be more likely reduced rather than oxidized, right? And if you have a negative reduction potential, that means, if we look at this, we have a negative 2.37. So magnesium 2 plus being reduced to neutral magnesium is not very favorable. It's not favorable, okay, because you have a negative reduction potential. But just like delta H, delta S, delta G, if you reverse the reaction, you flip the sign of the potential. And the reverse reaction would be an oxidation potential. Okay, so let's just look at this equation here. The forward reaction shows the reduction potential of magnesium 2 plus. But if we flip it and reverse the reaction and we change the sign to positive 2.37 volts, that would be the oxidation potential, not of magnesium 2 plus, but it would be the oxidation potential of magnesium. So let's understand, most of the time when you're given half reaction potentials, you're not given oxidation potentials. You're only given these. You're only given reduction potentials, okay? But every reduction potential has a built-in oxidation potential. All you have to do is flip it. So let's look at this one. The forward reaction and that voltage shows me the reduction potential of potassium ions. But if I reverse it and I change the sign to positive, then that would show the oxidation potential for solid potassium to form potassium 1 plus. So potassium 1 plus is not likely going to be reduced, but neutral potassium metal is very likely to be oxidized, because that would be a positive 2.925, all right? So again, a positive potential means it will happen. A negative potential means it's not likely to happen. The more negative, the less likely it is to happen. The more positive, the more likely it is to happen. And all these are reduction potentials. So the reactants of all these half reactions, this is showing the potential of them being reduced. But if we flip the arrow and flip the signs, it would tell us the oxidation potentials of everything on the product side of these reactions, the oxidation potential of the reverse reaction. Okay? So, oops, all right. All right, so, what does this potential tell me? It tells me that fluorine is likely to be reduced, and that makes sense. This being a very positive voltage should make sense to you because fluorine is the most electronegative element. It's good at pulling electrons to it, right? So fluorine is very likely to be reduced, but if we reversed it and made that a negative, that would tell us the oxidation potential of fluoride. So that's telling us that fluorine is good at gaining electrons, but fluoride is really bad at losing electrons, okay? And that should make sense to us, okay? So again, E red means reduction potential, and so if you reverse the reaction, that means you get oxidation potential. And anytime you flip a cell potential or flip a reaction, you flip the sign of the cell potential, okay? All right. So again, a negative potential means not favored. So if you have a negative oxidation potential, you're probably not going to be oxidized. If you have a negative reduction potential, you're probably not going to get reduced, okay? But what's the flip side of that? If you have a negative reduction potential, that means if you reverse the reaction, there's something in that reaction that has a positive oxidation potential. Or if you have a negative oxidation potential, if you flip that reaction, there's something in that reaction that has a positive reduction potential, okay? All right, so let's say this. Now let's talk about how to figure out what spontaneous reaction is going to occur, all right? So if we look at this, we have copper 2 plus 2 electrons yields solid copper. So that's the reduction potential of copper 2 plus. And that's positive, so that is favored. And then we have cadmium 2 plus 2 electrons yields cadmium. And notice that has a negative potential. Okay, so the reduction of cadmium 2 plus is not favored. Okay, so notice that we have 2 reduction reactions. Well, to figure out the spontaneous redox reaction, the thermodynamically favored redox reaction, the reaction that's going to occur when we mix all these things together, we can't just have 2 reduction potentials. One thing has to be reduction and the other thing has to be oxidation. So when you're given 2 reduction potentials and you're asked to find the reaction that's going to occur, the oxidation reduction reaction, understand you have to flip one of them. You have to, because you can't have 2 reductions. You can't have reduction without oxidation, or you can't have oxidation without reduction. So we're always just going to be given reduction potentials, but we got to flip one of them. Now, how do you know which one to flip? Well, just like Hess's law, all right, for delta H, delta S, and delta G, if you add a reduction reaction and an oxidation reaction, all you have to do is add the potentials, and that'll give you the overall potential of the reaction, all right? So the one to flip is the one that's going to ensure that when you add these 2 numbers together, you get a positive value. You get a positive value, okay? So if I flip this one, if I flip the top one, that'll be a negative 0.34, and then I'll be a negative 0.34 plus a negative 0.4, and that would end up with a negative cell potential. So that wouldn't be spontaneous. But if I flip this one, if I reverse this one, now I'm going to have a positive 0.4, and then I'll add 0.34 plus positive 0.4, and that'll give me the overall potential for this oxidation reaction. So all I have to do is flip this, make sure that electrons are the same so they end up canceling out. And so if I reverse this reaction and I add the 2 together, the electrons cancel out, and I get this reaction, and the overall cell potential for this reaction is going to be E ox plus E red, and in this case that would equal 0.34. The E ox would be 0.4 positive 0.40 plus 0.34, and that would give us 0.74 volts. Okay, so this oxidation reduction reaction would be the spontaneous oxidation reduction reaction because it has a positive cell potential. Okay. All right. So let's talk about how a battery works. All right. So let's say we wanted to make a battery out of copper and cadmium. Okay. Well, we know that this is the spontaneous reaction. So cadmium would lose electrons and copper would gain electrons. And so the cadmium would transfer its electrons to copper. And so all we would have to do is put the cadmium components in one place, put the copper components in another place, and connect them with something that conducts electricity. And spontaneously, the cadmium would push its electrons across that connection, and copper 2+ would pull those electrons across that connection, and you would get voltage. Okay, and that voltage, if you're at standard conditions, would be 0.74 volts. Okay, so separate the components. You got the oxidation half, the reduction half. We call the oxidation half where oxidation occurs, that's called the anode, and the reduction half is called the cathode. Electrons always flow from anode to cathode. Okay. Now there's other stuff that has to happen, but this is, the simplest way to think about it. Now there's other things you have to do to make sure, to ensure the steady flow of electrons, but this is essentially the start of it, right? Here's our idea. Now how do we make it actually work? You know what I'm saying? Okay. So let's look at a galvanic cell setup, okay? So here we got solid copper and copper ions in solution, and over here we got solid silver and silver ions in solution. And it's telling us that the electrons are flowing from the copper to the silver. Now what's really happening is the electrons are coming from the solid neutral copper, okay? And as that solid neutral copper pushes its electrons away, the copper solid becomes copper 2+ ions in solution, okay? And so notice this is where electrons are leaving. Electrons being produced is oxidation, so this is our anode half, okay? So the electrons go across the wire towards our silver, but it's not reducing the silver solid, it's reducing the silver ions that are in solution. And so as that electron comes down into this cell and adds itself to this silver plus ion, the silver plus ion becomes solid neutral silver, and it happens right at the surface of the electrode, and the silver will plate onto this electrode, okay? Now the other things we have in here are something called a salt bridge. The salt bridge ensures that the balance of charge stays, balanced, that charge stays balanced within the battery, because if you think about it, as electrons leave this compartment, this side is going to become very positive, and as electrons go to this side is going to become very negative. And it's going to be impossible if you get a very high negative charge buildup over here, electrons aren't going to want to flow towards a negative charge, if that makes sense, right? And they'll be more attracted to this side if it's positively charged. So a salt bridge has ions in it, okay, hence the name salt. It has ions in it, and the ions flow towards each compartment to keep it balanced. So as this side becomes positive, anions from the salt bridge flow to the anode to keep the charge balanced. And then cations from the salt bridge flow to the cathode to keep that charge balanced. And so as long as you can keep the balance of charge, the electrons will flow. And then you attach your, fan to it or whatever, and you can use your electricity there. Okay. Let's see. So here you can kind of see, as here's a zinc copper battery. Electrons are flowing from the zinc anode to the copper cathode, but it's the zinc cathode, which is the solid zinc metal here. notice how over time you lose some of that metal because the zinc is dissolving into solution as zinc 2 plus because it pushed electrons away from it. So the solid zinc turns into zinc 2 plus and it dissolves into the solution. And so we lose mass at the anode. But notice that as the electrons come in, again, they're not reducing the solid copper, they're reducing the copper 2 plus ions on the surface of the electrode. And you start to get extra copper atoms on that electrode. So notice how the copper electrode started to gain mass because copper 2 plus ions were plating onto them, okay? And then we got our salt bridge to maintain the balance of charge. And remember, anions from the salt bridge always flow to the anode, anions to the anode, cations to the cathode, okay? And then how did we get this voltage number? Well, we probably looked up the reduction potentials, okay? Now, here's the oxidation half reaction. To figure out what that potential is, you would have to go to your Appendix E and find the zinc reduction potential and reverse it. So let me show you what I'm saying. So look, we want zinc solid yields zinc 2 plus 2 electrons. But if we go to Appendix E, okay, let's find the zinc one. Where is it? It's gotta be here. There we go, right at the bottom, all right? So notice, this is the reverse of the reaction we want. But if we flip this reaction, we have the oxidation reaction that we want. And so we would flip that to positive we'll say 0.76, okay? Because we'll reverse that reaction. And then notice that the reduction half reaction was copper 2 plus being reduced to solid copper. So let's go back to our Appendix E and look up that potential of copper. So this reaction, that's positive 0.34. So if you take 0.34 plus 0.76, that's how we get that voltage, right? Because it's the combination push-pull. It's E ox plus E red, and that's the standard voltage of that battery, okay? All right, so that's essentially the stuff you need to know. I would strongly suggest one thing real quick, just make sure you understand Hess's law with cell potential because it's slightly different than Hess's law with thermodynamics, okay? So just like thermodynamics, when we reverse a reaction, we flip the sign. So if I reverse this reaction, this would become positive, right? And also just like thermodynamics, if I added two equations up, like if it was delta H, I would add their delta H's up. If it was delta S, I would add their delta S's up and their delta G's up. But if it's cell potential, you also add them up, okay? Remember, equilibrium constant, you multiply them. Cell potential, you add, just like the thermodynamics things. But the one thing that's different about cell potential compared to the thermodynamics is, let's understand, to make this a balanced redox reaction, we would have to multiply this reaction by 2, and we would have to multiply this reaction by 3 so that the number of electrons are the same, so they cancel out, right? But whenever you multiply a reaction, you don't change the cell potential. The cell potential is intensive. It doesn't depend on amount. It's intensive. So if this were delta H and I tripled this, I would have to triple the delta H. But if it's cell potential, if I triple this, I'm just going to keep this value the same. So slight difference. So we really want to understand Hess's law the three different ways. We got the thermodynamic way, and it's the same for delta H, delta G, and delta S, right? We got the equilibrium constant way, and now we have the cell potential way. And cell potential is very much like the thermodynamics Hess's law, but with one exception: we don't. If we double the reaction, we don't adjust the cell potential. If we half the reaction, we don't change the cell potential. The only time the cell potential changes is when you flip the reaction, and all you do is flip the sign. All right, so that's just a big, just a quick side note there. So that's essentially what you need to know. It takes a lot of practice, and hopefully you understood what I was talking about. But if not, check the PowerPoint, go through the guided notes, and we'll do more practice in class. All right. All right. Sorry about that. I'm getting a lot of emails right now, so I'll check that out. But anyway, that's kind of what we covered in class today. Those are kind of the important hits. Hopefully you can take that and use it to get a head start. Not a head start, but to kind of stay caught up on the current stuff. So remember our system. Our system is, man, I'm getting a lot of emails. Our system is, for the rest of the school year, you know, until May 2nd, is to stay caught up on current stuff. Don't miss a due date on current stuff. And then at the same time, if you're behind, you got to catch up. All right. But let's stay caught up on current stuff. You're going to have some class time to work on things and that kind of thing. So, system over goals. If you work the system, you'll meet your goals. All right? Man. All right. Stop.